Hey everyone, today we're going to be talking about design planning. So before you even get started with any design, any circuit choices, anything like that, you have to decide what are you going to make and how are you going to make it. So going through the steps of design planning before you do the actual design. So define the goals for your projects. What are you trying to make? What is the scope of the project? Talk to other people on the project if you're working with multiple people, like mechanical engineers, software engineers. What does your PCB need to accomplish? Like what are the absolute minimum goals? What inputs will it have? What outputs will it have? Get as much information as possible from others working on the project as soon as possible. Hold a ton of design reviews, because it's much easier to make a decision now than to try to change your design later after you've realized that, oh, someone else forgot to tell me that I needed this much power or something like that. So just try to get as much information as possible right up front. First things first, something to consider is power. So any electronics you have will require a power source. Is it going to be plugged into the wall? Is it going to be running off a battery? Are you going to have some kind of like charging? I would highly suggest not plugging things directly into the wall and using like a converter. Use some kind of converter to convert to like a lower DC voltage. How much power is this thing going to draw? What are the maximum required voltages and currents? Will you need to regulate voltage on board? Like, will you need to regulate AC to DC, or will you be stepping down 5 volts to 3 volts, or 24 volts to 5 volts? If it's really high power, you can use like thicker copper on the boards, depending on the ability of the manufacturer. So you'll need to be defining like think with that for your stack up. So how do you determine these requirements? How do you know what voltage and current you need? This is a cyclic process based on the components that you need. So maybe someone else will be telling you we're using this motor, or we're using this power source, and you'll have to work it out from there. The bigger, like power heavy components are usually going to set these limits, and you're always going to want to use a higher current rating than you think. So if the motor is rated to 10 amps, make sure all your components are rated to 12. You just don't want spikes ruining anything, and it's not a huge difference. If you have more than one voltage level, you can regulate up or down using designated integrated circuits, and we're going to go over that a little bit more in a later slide. So yeah, this slide actually. How do you regulate voltage? If you have one voltage you want to switch down to or switch up to, like how would you go about doing that? There are two different kinds of ways of doing this, and one is a linear regulator and one is a switching regulator. You'll learn a lot more about this in later circuits class if you're taking them, but the general idea is a linear regulator is like a very simple, small, cheap way to step down voltage on like a low delta. So 5 volts to 3 volts, or 12 volts to 5 volts, and in low current situations. So if you're drawing 10 amps, this is not a good idea. And the reason for that is this efficiency curve here. Linear regulators are a lot less efficient than switching converters, which we'll go over in a second. They're a lot less efficient, so you're going to be burning a ton of power. If you're losing like 40% of your power, that's going to heat, and so you're just going to burn up that regulator and waste a ton of power, especially if you're on a battery. That can be really disastrous for your battery life. One thing is they are very low noise, so if you need like a really solid, like relatively noiseless voltage level, linear regulators are a great way to go. These are also sometimes called LDOs, and LDO stands for low dropout. So that just means there's like a small difference in what you're regulating to. Switching regulators are the other kind, switching converters. They can step up or down, whereas a linear regulator can only step down. So this could go from 24 volts to 48 volts. These are hugely more efficient, and this curve is kind of a little bit arbitrary, honestly. You can get higher or lower efficiency than this depending on the converter that you use. They're a lot more complex and often require like external components for things like filtering. Yeah, we won't go into that too much, but they often require like extra circuitry around them. Whereas a linear regulator will just be voltage in, voltage out, maybe a few capacitors on there for filtering, but this will require like inductors and all that kind of thing. It's a little more complicated to work with, but you can do much higher power. So if you need to draw 10 amps for a motor or something like that, you're going to want to use one of these. And this is what will be in, if you have a power, like an AC/DC power source, most of them are going to be this for high current. Yeah, much higher efficiency, but they do have a switching. So basically how they work is by turning on and off the voltage and then filtering it out, which means that you do have some flicker on the power source. So you can at this frequency of switching. So it can be a little noisier, but for something like a motor, it's not as important as it's for a microcontroller, which is a lot more sensitive electronically. Okay, so let's say you're going off a battery. What kind of batteries are we looking at? What are the options? Batteries are great for anything you anything you have to move around and don't want to have stationary plugged into a wall. So you wouldn't have a battery on a 3D printer, but on a watch or a phone, you have to have a battery because otherwise it does not work globally. So there's a bunch of different kinds of battery types. You have like lithium technologies, which are very high energy density. And the problem is they are kind of volatile, so they can be dangerous to charge incorrectly, or if you puncture them at all, you can have like explosive results. So lithium is really good for like high density, but maybe not great for beginning prototyping and that kind of thing. Coin cells are what you're using on the boards I gave you. Those little coin cell batteries. They literally look like a nickel. They're very small, very cheap. They don't have a huge battery capacity, so if you leave that board on overnight, it will be dead. It's only going to last for a few hours overall, and you can't recharge them. There are some rechargeable coin cells, but not a common thing. You just buy them and toss them. You have like typical like for your flashlight batteries, right? Your 9 volts and your AA's and your AAA's and your these are really cheap, easy to find, really safe because you could like have a baby put it in their mouth and it'd be fine. Sometimes they're rechargeable, but they're usually pretty low density and low capacity. You have to change your flashlight batteries every few years, and they sometimes leak that like white stuff. Unideal. USB battery packs are pretty great. We use this often like some like ECE classes because they're rechargeable. They can be pretty large and last for a long time. But they are pretty big. So not great for like if you have a drone, for instance, you're not going to want to use a USB battery pack because that's going to be super heavy because it has all the circuitry to charge that battery, and they're just generally very large. And then nickel metal hydride, just another kind of small, easy, low density battery. Okay, so what's gonna run your device? What is the logic? What is the processing unit on your device? If it's like a really dumb circuit, like you're just blinking an LED, or when you touch something, you don't really need a whole microcontroller for that. Most boards, however, will be more complicated than that and will require some kind of control device for logic to program. So if it's something pretty simple, like we're doing in this class, you can use just a simple microcontroller. Usually I would go for more of like a well-documented, commonly used microcontroller at first, because if you're new to microcontrollers, it can be very difficult to understand these 400-page data sheets. So for instance, in this class, we're using an Atmega 328P. It is a microcontroller on the Arduino. It is very well documented. People have been working with this for years, very, very, very frequently, and you don't have to figure out every aspect of it to get it working at first. A bunch of different things you should think about when you're deciding a microcontroller. Power level, so what's it working at? Is it like an ultra low power one, like 1.8 volts? Does it need 5 volts because it's a higher power one? What's the core processor? Is it ARM? If you don't know too much about that yet, that's okay. It's more of a computer architecture kind of thing. How many inputs and outputs does it have? If you're running 5 devices, you can't have only 4 output pins because that will not work. And if you need sensors to be reporting to it, like does it have enough I2C ports or SPI or whatever it is that you're using? Does it have that at all? Some microcontrollers don't have SPI interfaces built in, or an ADC, for instance. If you want to use a potentiometer like we talked about in the previous lectures, if you want to use a potentiometer or some kind of sensor that reports an analog voltage, does it have enough ADCs for all the sensors that you have? And then memory size, how big is the program going on this, how many things are connecting to it, how much does it need to do at once? And then a billion other criteria that if you get more into microcontrollers, you'll learn more about. But that's the general overview of picking generally a microcontroller. Okay, next something to think about would be active components. So are there motors, LEDs, sound systems, LCDs, potentiometers? You need to think about what kind of connections do they have, how much power do they draw, how will they be mounted to the board. If you're picking an LCD that has like a huge mount or some kind of mount that is incompatible with a PCB, not ideal for putting on this project. If it's drawing too much power for your system, also not ideal. Like we just talked about, what kind of inputs and outputs are they going to require? Do you need an ADC? Do you need a DAC? Do you need I2C, SPI? if you're a microcontroller, if you design a product and you just want to add a little sensor to it, and okay, it uses SPI, but your board doesn't have SPI, well, pick something else. There's tons of sensors out there that could use something else. Or you could, again, pick your MCU for your devices. This is, again, a cyclic process that we're going through. Yeah, again, if you have too many devices like sensors that can't be all on a bus, so like, like SPI, right? So if you have a serial device, make sure you have enough ports on the microcontroller to support all those devices. You can't have 6 serial devices on a MCU with only 2 serial ports. That's incompatible. Okay, connectors. Again, what are you connecting to this board? Do you need to mount the LCD directly to the board, or are you just connecting with a connector and then mounting it to a chassis? How are you connecting power? Power is a really important one, how to connect. You're gonna wanna set up, you're gonna wanna, first of all, use a connector that is directional, so you can't plug in power backwards. And how are you connecting power? One thing to think about is, do you need reverse polarity protection? Is it likely that you're gonna like plug this in backwards or plug it in incorrectly, or something gonna maybe ESD protection, which is like a shock, like electric shocking protection. If you're doing anything that will not be permanently mounted, be careful to use strong enough connectors. So anything that's moving around or being pulled on it anyway. It's often useful to use directional or keyed connectors, so that's something you can't plug in the wrong way. It has some kind of key on it that will prevent it from being plugged in the opposite direction. Really useful for power, so you can't reverse power the board and fry components, especially with like something like a lithium technology. That's hugely important for not breaking your battery and breaking your board. So this is just a quick overview of things that might be useful to think about before you even start. And again, this is just electrical considerations, but then talk to your mechanical engineers, talk to your software engineers. Your software engineers need a certain amount of memory or a certain technology for them to program the firmware onto the microcontroller. Your mechanical engineers need need to maintain a certain power, or do they need certain components, or any thermal considerations? You need a heat sink on your board, that kind of thing. So talk to other people on the project. If it's just you and you're doing a small project, just think about all of these things before you even start drawing up a schematic, before you pick actual components. Just think about these things. Yeah. And next we will get on to the first steps of actually designing PCBs. Now this has all been mostly background information, but the next lecture will be about actually designing components in CAD.